Hello everyone, it's me, Professor Aaron Albert, here again with Lesson 31. Let's learn some econ. So last time we talked about games, we talked about simple static games, and we found pure strategy Nash equilibriums. What we're going to do today is we're going to show you how to find mixed strategy Nash equilibriums, which are important but a little more nuanced. Alright, so the first thing to remember is that actions and strategies could be different things, and in fact will be different things when we're playing mixed strategies. So you'll remember that player 1 in a 2x2 box like this could either go up or down. Player 1 can either go left or right. Up, down is the actions available to player 1. Left, right is the actions available to player 2. And now if they're playing pure strategies, strategies that are apparent are always play up, always play down for player 1, and either always play left or always play right for player 2. However, note that you can mix, i.e. always play up, always play down, and flip a coin becomes a much bigger option set, right? We could say, let's play up with 0.1%, let's play up with 4%, let's play up with 25%, and then play down the rest of the time. This opens up a very large set of possibilities. Now, as a quick warm-up practice, define for yourself what an action is for each player in rock, paper, scissors. Define a strategy. Give me one pure strategy and give me one mixed strategy. Then find a friend. Try your pure strategy. Do best out of 5. Try a mixed strategy. And then draw the payoff matrix. Good luck. All right. So hopefully you had a little fun remembering what rock, paper, scissors look like. In short, don't play pure strategies in rock, paper, scissors. You will not win very often. Okay, so next thing we should do is talk about what mixed strategies exactly are. A mixed strategy is defined as a strategy in which a player plays some % chance of each option, and the options are at least 2 of that are not 0. Obviously, the probabilities you use must sum to 1, and each option must be between 0 and 100%. So you can't say I'm going to play rock 150% of the time. Doesn't make any sense. Also note, if you ever are playing a game and there's a dominant strategy, don't mix. If you mix and you have a dominant strategy, when you solve it, you'll find probabilities outside the 0 to 100%, which doesn't make any sense. Don't do that. All right, so how do we get mixed strategy Nash equilibriums? It's a little counterintuitive. What we're going to try to do is solve for probabilities for Jeff and Mimi such that they choose some option to make the other player indifferent. Before we get to that, though, let's talk about this game. This game I use because, 1, it's a little funny, and 2, it's from the book. And the story goes as thus. Mimi and Jeff are romantically involved. Jeff is lazy and wants to be able to loaf all day long. He very much does not want to look for work. However, he also likes to be with Mimi. Mimi, presumably his lady friend, and he likes her to stay with him. Mimi, on the other hand, wants Jeff to stay with her and likes to be a supporting partner. Therefore, she likes to support Jeff and does not like to not support Jeff. However, she doesn't want a deadbeat man friend, so she would prefer that he looks for work and doesn't loaf. This results in a situation where Jeff very much wants to loaf and not look for work and be supported by Mimi. Mimi wants to support Jeff and have him look for work so they can stay together and be happy. In order to make a mixed strategy Nash equilibrium, what we need to do is find, let's call it a theta for Mimi, that she supports him with some theta probability, such that Jeff is indifferent between looking for work and not. That is, if Mimi plays support theta of the time, Jeff will not care, i.e. will get the same utility if he looks for work or does not. Meanwhile, we will look for an alpha for Jeff, i.e. a probability he looks for work, such that he doesn't care if he looks for work, such that Mimi doesn't care if she supports him or not. So this can be a little confusing because Jeff is choosing probabilities based on Mimi's utility levels, and Mimi's choosing probabilities based on Jeff's utility levels. So let's do it. First things first, let's let Mimi support him theta of the time, not support him 1 minus theta of the time. If Jeff looks for work, what utilities does he get? Well, it looks to me like he would get 2 theta plus 1 times 1 minus theta utils. You'll note we also just said we want to make sure his utility is the same, looking for work or not. So that must be equal to what he gets if he loafs. If Jeff loafs, he gets 4 times theta utils plus 0 times 1 minus theta utils. Therefore, in order for Mimi to make Jeff indifferent between looking for work and loafing, it must be that 2 theta plus 1 minus theta equals 4 theta. Now all we have to do is solve out for our theta. If we do that, and I do it correctly, you'll note that we have 2 theta plus 1 minus theta must equal 4 theta. Therefore, 1 equals 3 theta. Therefore, theta equals 1/3. This means if Mimi chooses to support Jeff 1/3 of the time, Jeff will not care whether he looks for work or not. Let's see if I did it right. Hey, look at that. Then, all we have to do is the same thing for Jeff. Let's have Jeff find some alpha be the probability he looks for work, and 1 minus alpha probability he loafs. He's going to pick this alpha such that Mimi doesn't care if she supports him or not. Doing that, first thing we should ask is what is Mimi's utility if she supports him and he plays this game? Well, she'll get 4 alpha of the time minus 1 utility, 1 minus alpha of the time. That must be equal to alpha times -1 plus 0. Then all we have to do, as before, is just solve for alpha. I've got 4 alpha minus 1 plus an alpha equals minus alpha. So then I've got 4 alpha, 5 alpha, 6 alpha. So 6 alpha equals 1 implies alpha equals 1/6. Again, what does this mean? This means if Jeff looks for work 1/6 of the time, Mimi will not care if she supports him or not. So next, you might be asking, well, why did we do this weird thing where we're choosing utilities if the other person doesn't care? If Mimi supports 1/3 of the time, and Jeff loafs 1/6 of the time, then does it matter which either of them do? I think the answer is no, right? Mimi plays support 1/3 of the time, and Jeff doesn't care if he looks for work or not, therefore he has no reason to deviate. That is, his utility for looking for work or loafing are identical. Similarly, if Jeff looks for work 1/6 of the time, then Mimi doesn't care if she supports him or not. Therefore, she has no incentive to deviate from any strategy. Therefore, she has no incentive to deviate from the 1/3 support him strategy. Therefore, we've found a mixed strategy Nash equilibrium. All right, let's do one more. This time, do it on your own first. Here we have another perfect game to find mixing in, and I will show you one more tip first. In this game, we will note that firm 1 and firm 2 are quote-unquote symmetric. That is, if I were to relabel and redraw this game such that the payoffs for firm 1 and firm 2 are reversed, i.e. I put the column player where the row player is and vice versa, the box will be exactly the same. To check that, you'll see in this corner they are the same, in this corner they're the same, and in this corner and this corner they just have the opposite payoffs. Therefore, we know if we defined firm 1 strategy as alpha 1 minus alpha, firm 2 strategy as beta 1 minus beta, our alpha has to equal our beta because they're doing exactly the same things. If that's the case, if you find a game that is symmetric, you only have to solve for one of the players. They're both going to do exactly the same thing. So solve for alpha, or beta if you prefer, and let me know how you do. All right, let me give a rush job. Let's see how this goes. If firm 1 enters alpha of the time, does not enter alpha of the time, enters 1 minus alpha of the time, what are firm 2's utils? Well, it looks like they would get, if they do not enter, 0 plus 0, and that must be equal to alpha times 1 minus 1 times 1 minus alpha. Therefore, 0 equals alpha minus 1 plus alpha. Therefore, 2 alpha equals 1. Therefore, alpha equals 1/2. By symmetry, we know that beta equals 1/2. Therefore, if firm 1 and firm 2 each enter, and thus also do not enter 1/2 of the time, neither will care what the other one does when we have a mixed strategy Nash equilibrium. Okay, that brings us to our practice slide. See if you can find the mixed strategy Nash equilibrium in each of these. Let me know how you do. Also, pro tip, you'll note each of these are symmetric, so you only have to solve for one player, unless you want to be extra thorough. Good luck, guys. See you next time. Bye.